Hello, everyone. I'm Zhengyang. I'm from University of Utah. So I'm advised by Professor Zhengyang Liu. In this talk, I will present the research project I'm working on, Minotaur. Minotaur is an enumeration-based synthesizing superoptimizer that focuses on optimizing SIMD programs. So I will start my talk with some background. From hardware perspective, today vector processors can be found everywhere, from high-performance computing clusters to mobile devices, and they deliver very high peak performance. And from software perspective, developers has taken a lot of effort creating frameworks and softwares and compiler supports to take advantage of those new hardware instructions. However, as the hardware becomes more and more special or customized, the generated code from those software solutions often cannot fully unleash the power of those hardwares. So to better optimize programs that are targeting those new customized vector processors, SIMD operations are supported in major compilers. For example, most arithmetic operations in LLVM middle end can be used on vectors. LLVM also supports x86 and neon vector intrinsics. It also supports data movement instruction, like, for example, such as shuffle vector, insert element, and extract element. Those instructions allow optimization paths to operate on the SIMD instructions directly from middle end. And this further enables compiler developers to write rules for optimizing the programs with those using those high customized instructions. However, this approach requires expert time, and those rules are often less developed, and this leads to missed optimizations. So let's take a look at how vector instructions are being optimized in the LLVM middle end. First, LLVM has instant combine. Instant combine is a people optimization path, and it performs people optimizations on the program. Most people optimization rules in the instant combine are designed for scalar operations. Those rules can be also used or applied to element-wise vector operations. So here the limitation is very obvious. It cannot handle operations with interlane communications. LLVM also has this vector combine path. This path is similar to instant combine, and it merges vector operations by following several rewrite rules. And those rules are designed, some of those rules are designed to handle shuffles that are not element-wise. However, this path is less mature than instant combine, and this is one of the reasons why we developed Minotaur. Here is an example showing how easily an optimization is missed. Here is a loop that calculates the difference between adjacent integers. And it is a very simple loop, as you can see on this slide. And this loop is found in libYuV image scaling library. So LLVM generates this code when compiled with -03 with auto vectorizer turned on. Here, we assume all the integers are already loaded into the vectors. And what this code does is it first instructs the elements in the even lane to a new register and elements in the old lanes to another register. And the program unpacks those two registers with zero intention. And finally, we subtract those two values to get the final result. LLVM cannot further optimize this piece of code, both by middle end and by the code generation. We cannot do further to this code. But meanwhile, Intel SSE has this nice FMA instruction, PMADDWD, This instruction multiplies packed 16-bit integers from two vectors and then adds the adjacent result together. But what do we do with this instruction in the context of our example? So if we call PMADDWD on vector, the input vector and a constant vector containing interleaved one and positive ones and negative ones, we will get the exact same result as the shuffle zero extension abstract version. The old version needs 11 micro operations, and the new PMADDWD version only needs 3 micro operations. This rewrite will save us 8 micro operations. So in this case, we need a rewrite rule that in our middle end, as this slide shows, to rewrite shuffle zero extension subtract into an intrinsic call to PMADDWD. In this call, we call the slower sequence, or the sequence found in the original program, the left-hand side, and we call the optimized sequence the right-hand side. For compiler developers, coming up with such rules can be very tricky. So we want to know, is it possible to automatically derive instruction combining rules for SIMD instructions? To solve this question, we developed the Minotaur Superoptimizer. Minotaur is designed to discover new vector optimization rules using program synthesis. It consists of 5 different parts. As real-world programs may be large, and the program synthesis cannot really scale up to the whole program synthesis, we developed a SSA-based program slicer that split the functions into small sequences. Minotaur also has an enumerator, which automatically generates rewrites for the slices. The rewrite generated by enumerator at this stage may not be correct, and the correctness of each generated rewrite is verified by a refinement checker. We also have a cost model based on LLVM MCA, which helps us to predict whether a rewrite is profitable. And finally, Minotaur caches the synthesis result for later reuse. In the following slide, I will talk about each part in detail, and later I will show a few rewrite examples found by our Superoptimizer, and then I will show the performance end-to-end performance numbers. To limit the complexity of program synthesis, we implemented a program slicer that split the input program into small slices. The program slicer uses a search algorithm that collects the instruction with a SISA use depth chain. Our slicer supports extracting control flow direction and memory operations. All the values that are unknown to the synthesizer or beyond the depth limit, predefined depth limit, are listed as free variables. After we split the program into small slices, we want to find a right-hand side that is a cheaper implementation of the right-hand side. Here, a right-hand side may be a constant, or some existing value in the left-hand side, or some new instructions. So we do a search. We search the right-hand side in the order of increasing complexity. Here is a picture showing the search we are doing. So we enumerate all the possible right-hand side, trying to find a cheaper implementation of left-hand side. Clearly, most right-hand side here is not valid. We need to keep trying until we find a good one. So you may here ask, how does our enumeration algorithm scale? And of course, it scales very poorly. It is an exponential algorithm, and typically, if we allow one new instruction in the right-hand side, we will be enumerating hundreds of rewrite. And if we allow 2 new instructions in the right-hand side, we will be enumerating 1,000 of rewrites. However, most real-world people optimization rules in major compilers are only creating 1 to 2 new instructions. And the 1,000 of rewrite is totally acceptable if we have, what's the, so, which, I'm sorry about this situation. Okay. Okay. Let me just restart. Restart Chrome.
Okay.
Okay. So let's continue. What I was talking about is 1,000 of rewrites is totally acceptable if we have a powerful multi-core machine for this task and if we parallel the search. In the next slide, I will show how to check the correctness for a rewrite. Here, in this work, we used the Alive2 translation validator for this task. Alive2 was originally designed for finding bugs in LLVM. Given a pair of LLVM functions, Alive2 proves if the source function can be replaced with the target function or not. In Minotaur, we use Alive2 to check if right-hand side is a valid rewrite of left-hand side. So here you may ask, how does it handle new instruction that has immediate constant in the right-hand side? For example, consider this rewrite. Assume the enumerator generates a right-hand side which has a shift left operation. What constant should we put for that C? Should we explicitly enumerate all the possible values for that C? The answer is that will be stupid. In our work, we rely on SIMD solving to synthesize those immediate constant in the right-hand side. There are several approaches for synthesizing immediate constant in the right-hand side. We may just encode the problem in the solver with a naive exist for all synthesis query. That is, if there exists any constant, right-hand side refines the left-hand side for every possible input. Minotaur implement this approach, and in this code, you will find several examples of the synthesized constant. In order for Alive2 to be able to reason in vector programs, we need to teach Alive2 the semantics of those vector operations. Till now, the semantics for all platform-independent vector operations, such as trivial add sub, multiply, are all implemented, and all other vector platform-independent operations, such as insert element, shuffle vector, are also implemented and open source at the main Alive2 repository. And I also hand-coded the semantic of most x86 integer non-memory intrinsics. Those intrinsics are highly reusable. It only takes 2,500 lines of code to implement those new semantics. After the refinement check, we have a valid rewrite. So the question here becomes, is that right-hand side really cheaper than the left-hand side? So we need to use a custom model to check whether the rewrite performance better than the original program in the real-world runtime. And the LLVM IR is not a good choice for predicting runtime performance. Instead, we compare both left-hand side and right-hand side to assembly, and we call the LLVM machine code analyzer. And we check the number of micro operations required as the cost of our program. So I hope this covers all the detail you need to know about Minotaur. In the following slide, I will show a couple of examples and show the performance and performance numbers. So this example is found when we use Minotaur to optimize Perl bench inspect CPU 2017 benchmark suite. So the left-hand side tries to zero extend each lane in both vectors, and it calls the get average intrinsic on those two new vectors. Then it calls the trunk to convert the result back from 16 bits to 8 bits. And Minotaur found the round trip is not necessary, and the left-hand side can be replaced with this just a SIC variant of the get average function intrinsic. This rewrite reduces the cost from 4 micro operations to 1. This code sequence is found when compiling the GNU multi-precision library using our Superoptimizer. Minotaur found out that code on the left-hand side is a pop count routine. The input is a 64 bits vector, and the pop count is performed in byte. According to LLVM MC, this rewrite reduces the cost from 19 micro operations to 13. Here we compiled some real-world software programs, and here is the performance numbers. We compiled the GNU multi-precision library, or GMP, with Minotaur, and this plot shows the average speedups of GMP bench test rate. We got an average of 4% speedups. The benchmark with the largest speedup is multiplying to 128-bit numbers, and the speedup is about 15%. We compiled the LLVM image scaling library with Minotaur, and this plot shows the speedup of the LLVM test rate. We got an average of 0.3 speedups for those 2,000 test cases. The largest speedup is about 40%. We also compiled the spec CPU 17 benchmark suite with Minotaur as well. The average speedup is about 1.2. With those examples and benchmark result, here I conclude my talk with the possible future work we have planned to do. To reuse those synthesized rules, I plan to create a compiler that can lower the synthesized combining rules to LLVM vector combine code. We will try to prune the search space to have the Minotaur scale up to synthesizing 3 or more instructions. And finally, we will add support for floating point operations. And Minotaur is currently in active development, and the code is open source at this link. So I'm graduating next year. So if you are interested in me, so you can find my CV at this link or the QR code. So this is all of my talk. Thanks for listening.
Thanks, Zhengyang. That was amazing talk. Like, there were good performance numbers, right? So if you have questions, you can queue behind these mics, or I can bring this mic to you.
How does this affect the time to compile?
As I mentioned, this the enumeration algorithm is exponential. So I can list a few numbers. So compiling GNU multiplication library takes 6 hours to finish. Compiling the whole integer part of spec 17 benchmark requires 30 hours. And compiling the whole LLVM library takes 48 hours. About.
Thank you. And as a follow-up to that, have you considered like trying to offload the compiled time, like when it compiles, to like identifying certain transformations and then making those into peepholes that sort of exist already, so you're not searching for them?
Yeah, we have a cache that stores the synthesized result. So if the synthesized result is already in cache, we will take minutes for compiling those libraries
Thank you.
and benchmarks. Yeah, sure.
Yeah, great talk. Thank you very much. So, first of all, I wanted to ask, so when you say Z3 is the bottleneck, so this is the time where you enumerate a new instruction, and then you're going to look for possible constants that make the semantics of the instruction work with the original one, right?
Yes.
So, have you tried, instead of, because obviously the SMT file is going to be quite large, it's going to take quite a long time to do the search in SMT, instead of first calling the SMT, trying to just enumerate, most well-known constants instead of calling the SMT straight away, because a lot of the times what I found working in superoptimization is that the constants that you tend to use are sometimes most likely the obvious ones, like 1, 2,
Yes,
8,
yes.
64, etc.
Yeah.
So that would be a possible attempt to improve the things. The second thing is, why is this work, for example, not integrated with Super?
Oh, so we could, but so
I'm sorry?
we could have this implemented in Super, but this work implements a new program slicer that is able to extract the explicit control flow information, which is not implemented in Super, and also the slicer also extract memory operations. So that slicer is a totally new design. So and it's so that is a reason why.
Okay. The other question. Sorry. So last question. The other question is, when you compile it once, it takes 6 hours. You put it in a cache. You compile it again. It's going to be, it's going to be almost instantaneous, right?
Yes.
Okay. Yep. Thanks.
Yeah. That's.
Quick one because we're running out of time. You have implemented the semantics of those intrinsics for Alive, right?
Yes.
Could we use that to expand, like to do it the other way around, expand the intrinsics and actually replace them with generic code?
Yes. That's
That would be
totally.
nice.
Yeah. Only this the direction of transformation only depends on if the transformation actually has benefit. So it's pretty. Yeah.
For some people, getting rid of target-dependent
Yes.
intrinsics has
Yes.
benefit.
Yes. We have seen the scenarios where replacing the machine intrinsics with general code, we have some performance gains. So
Okay.
we will do that.
Perfect. Thank you.
In that direction.
Have you looked at where the regressions are coming from in your benchmarks? And maybe relatedly, have you looked into more sophisticated cost models that aren't just micro ops?
Yes, that's a very good question. So one of the major shortcomings from this work is the local optimal sequences may not be global optimal. So like they cannot predict if the port are occupied or not. and the result coming from the local ones may not truly reflects the real world situation. So that is one of the reasons why we have performance regressions. So for the for using the micro operation as a metric, so we also try to use the cycles as the metric, but we are still investigating if either of them is the right one to do, and this is some future work we have done.
Yeah, that makes sense. Thank you.
More questions need to go offline. Thank you for the amazing talk.
Sure,
Next
thank
talk
you.
will start in 5-ish minutes, 6:05. Thank you.